Hello, here for the ADVizE mini lecture where sampling, data, and inference meet. I'm Kristen Hunter Thompson. Let's jump in. So, as we're jumping in and thinking about sampling, inference, data, all of these things colliding together, I've got a phrase to share with you. Science is a probabilistic endeavor. So, what I want you to do is I want you to pause the recording and I want you to just think, what does that mean to you? How do you incorporate this into your approach of working with data now, right now, as you're working with data, or as you have been for the last couple of weeks? Then come back. Okay, so we've seen this before. Which plant is taller, right? We talked about this. This is a pretty, this is a numeracy. Once you know how to subtract 52 from 80 centimeters, this is deterministic. There is an answer once you know how to do the calculation. Which group is taller, right? We talked about is more complicated because it involves data, groups of values of information, and we need to make decisions. This lands us into the realm of probabilistic. So when we think deterministically about knowledge, then more research, more work, more data, or a lack of proof or proving something suggests that you've done something wrong, right? If you need more information to subtract 52 from 80, it's like, well, but you're going about, like, what are you doing? How are you going about it? Like, there's a simple way. There's a simple answer to that. But if you think probabilistically about the knowledge that you have, then more research, work, data, information is always needed because we can never prove anything. Having more values for plants in each of those different groups will help us better feel more confident, better sort of answer that, like, which group is taller. But we can never prove definitively that one group of plants is taller than the other. Because there could always be more plants, more information we could get in. The sample could be bigger. We could make a different decision on how we define taller. So this is probabilistic thinking. There's decisions that are always going and things are always happening. If we think deterministically about knowledge, then there's a right or a wrong answer, whether or not it is actually a deterministic thing that we are trying to do, like subtraction. Whereas if we think probabilistically about knowledge, then our conclusions are supported or not with the existing evidence that we have. And we, as humans, we really like to think deterministically. All of us really like to think deterministically, and especially our littles, our learners, our younger learners. So a great example is if the weather forecast says that there's a 70% chance of rain and it rains, people will often think or talk to one another about the forecast was right. But if it doesn't rain, then people often will think and talk to each other of like, oh man, the forecast was wrong. Like those weather people, they can never get it right. When in reality, the forecast was absolutely right. And in fact, the forecast is not right because it's just a probability of there was a 70% chance and a 70% chance of rain means there's also a 30% chance of non-rain. It's a prediction. It's a probability based on the information that we have at that time when it is made. It's not that it's right, like it's not that the weather person was right or wrong. It just is what it is based on the information that we have when we're making a prediction for it, a probability of the likelihood that it would rain or not rain. It's this funny thing that us humans, as soon as that number gets above 50%, we sort of think about like in terms of right or wrong, things like that. But this really influences how we make sense of data. And it comes back to one, our understanding of this kind of probability, probabilistic thinking, of kind of how we're making decisions, and the sample. Samples are important. So back in our first mini lecture, when we were talking about what are data, we talked about how data are a group of values. And whenever we're looking at a group and when we're comparing across groups, within a group, across groups, there's always variability. And that the data we have that we're working with is always a sample of the whole. We're hoping that it's representative. We hope that we're not missing too much, but we recognize that we are always missing something because it is just a sample that we have. So what that means is that we need to think about what kind of sample was used. When we're looking at visualizations, when we're looking at claims that are made, when we are trying to make claims from the data that we have, we need to think about what was our sample. Because we don't always have the data, we cannot measure it all, we have to think about who or what is in the sample. Is the sample big enough? How was the sample selected? What did we do before we even started collecting data to determine what data we would have on the outside? Because junk in is junk out. So if we don't have a very good representative, large enough sample going in, that's going to really limit what we can say coming out from those data. It doesn't make it impossible. It just really narrows the focus of what we can say. Samples need to be representative from the larger population. We can't, so this was long ago, the 2016 presidential election. We couldn't necessarily just call 10 people in the United States and get this answer. I mean, we could have come up with these percentages, but that wouldn't be representative of everybody in the United States. So when we're considering collecting our sample and what's in our sample, we got to think of a couple different ways that sample can kind of veer off of being representative. Think about the selection bias. Were the things that were measured, so either individual people in surveys or individual items in our in-class investigation or observations that we went out to measure out in the field, were they randomly selected or not? Ideally, they're randomly selected, not just I want to go observe birds and trees, so I'm going to go out and find all the trees that have birds and just going to record those. Because that's not really going to give us a representative sample of all trees that could have birds. It's just the trees that do have birds at that moment in time when we went out. When we're thinking about long-term studies, there's this thing called survivorship bias of kind of who falls out or what falls out over time. As we are trying to grow plants in the dark over long periods of time, some of them will die. That's an important piece of information, but we need to keep that in the sample to think about it. When we're asking people in our sort of social studies context, when we're doing surveys with people, there's a recall bias. It is really hard for us to actually remember every single detail. All of us, all humans, memories sort of shift and change over time, often in ways that are influenced by other things that have happened or what people have said. So we need to factor that in. There's sort of the healthy use bias, so kind of other confounding factors might be at play, driving the differences. So you didn't record information. That's what a confounding factor is. It's another variable that's influencing what you're measuring, but you didn't record on it. And then in the literature, there's this thing called publication bias, where people only submit papers to be published that have positive results. We don't often submit. It doesn't often get published when we found no result, which is still a result and can still be really important to think about. So if that's kind of about the sampling, then let's think about so what do we say from the data? How do we make some inferences? And what's really important to remember is that what we can or cannot say is dependent upon the data that we have. So what time, space, variables do we have data on? That's what we can make a claim about. What I can or cannot say about those things is dependent upon what data I have, not what data I want to have, not what data I think I have, but what data I actually have. So I cannot make a statement about climate change from a potential track of one hurricane. Looking across multiple hurricanes across multiple decades, more than 30 years or longer, then I could maybe say something about a effect of climate change on what we are observing in hurricane intensity. But one hurricane potential track, nope, all I can talk about is what might happen with that one hurricane in that place and time. Inference space is the boundary on what we can include in our claims from the data. So it's what we can say that is, because that is dependent upon what data we have. So this is a little bit of a wonky jargony thing. Our inference space is what claims we can make. Once we have made a claim from the data, then we can make an inference from those data, off of those data, to make a prediction going forward in time, to make a prediction for a different geographic region, to make a prediction for a different population, things like that. So it's this wonky thing. Our inference space determines what claim we can make. What claim we make, we can then make a conjecture, a prediction, or an inference off of that claim, off of those data, to a different situation. So what does this look like with students? Or what does this look like when we're looking at some data? So we could be asking the question, how does weather vary over time in one location? And maybe we're using these data from Indianapolis. So a student might say, August temperatures everywhere are. Well, our sample's only from Indianapolis, Indiana. So we can't say everywhere. Or we might say yearly temperatures in Indianapolis or temperatures in Indianapolis, but we only have data from August. So we can't say things about other months of the year. Or August temperatures in Indianapolis are. Great, we've got the place, we have the time, except we only have 14 years of data. So it can't be all time forever. We can only make a claim on the 14 years. Or this is what I was talking about with climate change. August temperatures in Indianapolis are XYZ because of climate change. 14 years is not a long enough time frame for us to talk about climate change. And so that is what we could say is August temperatures in Indianapolis have stayed pretty similar from 2004 to 2018, suggesting that maybe climate change is not having an impact on August temperatures. But more information would be needed to know about August temperatures starting in the 1950s, 80s, things like that, before we can make any claim about 2004 to 2018 going on in the temperature. So these are different examples of where we have a graph and we're trying to make a claim from the graph, and we need to sort of make sure that we're nuanced or sort of careful about what claim we're actually making that is really tied to the data that we have, staying within that inference space. And then being really clear, what is a claim that I'm making from the data? And then what is a prediction, a conjecture, a hypothesis, an inference that I'm making off of the data going forward? Just sort of a final note about this is make sure you do a gut check. Just because you can make a claim from the data does not mean that that claim is actually relevant to the real world. So pause and think about, once you've made that claim that's bounded by your inference space, does that relate, make sense, seem like it jives with the system or phenomenon that you're investigating? Does that pattern make sense? Do those numbers make sense? Does that conclusion make sense? Now, this can be hard when you don't know a lot about the system or phenomenon, but doing that kind of step back and thinking can be really helpful to be like, oh, okay, yeah, I can and want to make this claim from those data. So our sampling is really important. We always have variability. We think about kind of how our sample influences what we can see in our data, and then our data influences what we can say from the data, what claim that we can make from the data, and then we can make an inference off of the data. So I invite you to do some compass points. So pause the recording and think about S, what is your stance now on sampling and inference? E, what are some things that excite you about sampling and inference and thinking about that as it relates to your own data or going forward, helping your students work with data? W, what are some worries or things that you're worried about on thinking about your own sampling, making your own inferences, or helping students wrap their heads around this? And then finally, N, what else do you need to know or find out about sampling or inference to overcome these worries, to help you feel a little less worried about those pieces? There are a bunch of resources out there. Here are 4 that could help if you want to dive in a little bit more to this interplay between how our sample influences what data we have, how what data we have influences what claim we can make, and then like from the claim, how do we make an inference? These are 4 of many, many, many that are out there that I can recommend to you. And as always, Thank you for all that you're doing to make sense of your data, to dive in, to draw those inferences, to think about your sample. As always, if you have any questions, reach out. Happy to answer them.